Welcome back to MentorMe. Today we're diving into the fascinating world of Karnaugh maps or K-maps. Imagine having a magic tool that turns complex digital logic problems into simple, elegant solutions. Sounds incredible, right? K-maps are that magic tool. They're like a puzzle that, when solved, reveals the most efficient way to design and simplify digital circuits. Whether you're a beginner or a seasoned pro, mastering K-maps is going to definitely elevate your understanding of Boolean algebra and make your circuit designs more streamlined and powerful. If this video genuinely helped you tackle K-maps better, please subscribe to my channel and enjoy more of these. Starting off today, our agenda is going to be understanding the conversions of truth tables to K-maps and K-maps to Boolean expression, combinational logic circuits, and then back again from Boolean expressions to K-maps. So let's just dive right in. Start off with this truth table, which is the simplest form that has two input variables, A and B, and one output variable, which is Y. So starting off with the construction of the K-map, it's very simple. You basically be having two rows and two columns because you have two input variables. So you will be inserting the values of your input variables over here. So A takes the values of 0 and 1 at every instance, and B takes the values 0 and 1 as well. So let's fill out this truth table over here. So when A and B both are 0, you have your output Y. Let's fill that up in red. It's 0. When your input A is 0, which is this row, and your input B is 1, which is this column, you have a value of 1. And when your input is 1, which is this row, and your input B is 0, which is this column, you have 1 again. And for 1, 1, you have 1 again. So this is how you fill out your K-map. And coming out with an expression for Y requires the grouping of each 1. So 1 basically means when your output is true. So grouping this actually happens in the power of 2. So you can group 2 to the power 0, which is 1, 1, 2 to the power 2, which is 2 to the power 1, which is 2 ones, 2 to the power 2, which is 4, 2 to the power 3, which is 8, and so on. So this is the number of ones that you can group in your K-map. So following exactly this, let's actually move on to the grouping. We have 2 ones over here. And remember, you need to always go for the maximum possible number of ones in a group. So this is going to be one group, and this one has to also be grouped. You can overlap these groups, and that gives us, so how do we come up with a Boolean expression for either of this? So we see if A, so let me use a different color for this so that it's more clear. So when we're talking about this particular group, we have A, which is changing at both times, right? A changes from A takes 0 and A takes 1. But we have B, which does not change throughout this column. The value of B is always going to be 1. So we use a constant that doesn't change over a column or a row. So we have B coming from there. And we have another group, which is this particular group, and this gives us A, which is a constant value, but B keeps changing. B is not a constant. So that is how you come up with the Boolean expression for Y, which is going to give you A or B. That is exactly the expression of an OR gate. So when you're developing the combinational logic circuit for this, you all know that you start off with either one of the variables you might have, that is A, and you can have a not A, but in this case we don't. But when you're drawing your combinational logic circuits, always make sure this is there in case you have a complement of A and a complement of B, so that you could easily take off these as your output. So you have A coming off, which is right over this point, and you have B, which is right over this point, and both of them with an OR gate. This is going to be your output Y. So this is your combinational logic circuit. It's easy as that. So this is the simplest form that you can obtain, which is two input variables. Now we're going to solve the truth table with three input variables, namely A, B, and C. So how do we come up with a K-map for this particular truth table? So the K-map for this instance is going to involve three input variables, and we're going to fill them out based on the values of the output, Y. So in this case, there can be two ways to draw the columns and rows of your K-map. So for this particular example, I'm just going to go with 2 rows and 4 columns. So we're going to fill this up with our input variables. We have A, and we also have B and C. So A takes two values, 0 and 1. C, the combination of BC takes 4 values, which is either 0, 0, 0, 1, 1, 1, and 1, 0. So in this case, I just want to mention why 1, 1, that is basically 3, comes before 2. So this is actually not just binary, but this is gray code. So in gray code, we know that one bit changes at one time. So from 0 to 1, you see that the first bit is the only bit that has changed and no other bit has changed. But if you jump from 1 to 2 straight off, you know that this bit, your first bit, has changed from 1 to 0. So has your second bit from 0 to 1. So this cannot happen because only one bit at a time can change. That is why we replace these, we swap the two. When you go from 1 to 3, you see that this bit, first bit, is a constant, and only this bit has changed. So this is correct according to grayscale. And then we go from 3 to 2, where you see your second bit is a constant, and your first bit is the only one that has changed, which is also correct. So remember, when you're drawing K-maps, your 3 always comes before 2. So 1, 1 comes before 1, 0, and this is because it is a grayscale. So moving on to our K-map, let's fill this out, right? So we have the values that Y takes. I feel like we should just fill out the zeros so we can fill the remainders with 1. So for the combination of A being 0 and BC being 0, 0, which is A being 0, this particular row, and BC being 0, 0, that is this particular column. So the only overlapping position we have is this particular square. So going ahead with that, we fill that out with a 0. And we have A taking 1, B and C taking 0 and 1. which is this particular instance. And then we have 1, 1, 1 when A takes 1 and B, C takes 1, 1 as well. That is over here. And the rest of the combinations just give us 1. So we fill that out just like this. And now we need to group them. So remember what I mentioned about grouping? You can group 1 1s together, 2 1s together, 4 1s together, 8 1s together, and so on. You cannot group 3 1s together, even though that group seems bigger than 2. But now let's get ahead with the grouping. Let me use another color. So we have 3 1s over here, which we cannot group, but we have 2 1s over here. So let's go ahead with the 2 1s. And we have this particular one standing alone. So in this case, we can either group these two together. Use another color. We could either go with this option or we could go with this option. So either one is correct. In combinational logic circuits or solving K-maps, there is no hard and fast rule as you can only have one answer. Both of these options are correct, but I'm just going to go ahead with this option. And remember, we have this particular one standing alone, right? So remember that we can group them vertically. So this one keeps continuing, which means this one and this one is connected. You can group them like this. This one is grouped with this because 1 is always smaller than having 2. So 2 is our preferred option. So if you get a Boolean expression for that, you see that A does not keep changing. A is a constant value of 1, but B and C, B is 0 over here and 1 over here, so it's not a constant. But C is 0 in both instances, which is the complement of C. You see 0 is the complement of C. So in this case, we have A and we have C prime, which is the complement of C. Next, let's just come up with an expression for this particular group. You see that A is not a constant. A is 0 for this row and A is 1 for this row. But B and C is a constant. B is 1 and C is 0, which is the complement of C. So we have B and C prime. This is what we have over here. For our next group, which is this, you see that A is a constant of the complement of A. And B keeps changing, but C is once again just C over there. So this is the expression of our output, which we see A, C prime, A prime C, and B, C prime. This is our Boolean expression of our output. So what if you have to come up with the combinational logic circuit for this particular output? So remember, we have 3 variables, input variables, which is A, B, and C. And at times, they take the complement of each. So remember how I advised you to draw it. You have A. Just take out a NOT gate from it. That's going to be A. This is going to be our B. And this is going to be our C. We have B and we have our C over here with a NOT gate. So remember that whatever you take out from this spot is going to be A. Whatever you're going to take out from this spot is going to be the complement of A. Same goes with B and C as well. So our first character is going to be A. So you see that this is basically an AND gate. A and C complement. So you have A coming out and you have the complement of C, which is this point, and we have an AND gate. And we have the complement of A, and we have C, which is just plain old C, and we have an AND gate. Then we have B, which is exactly this, and we have the C prime, which is coming out of the NOT gate of C. And we have an AND gate over there, and we see that these three products are connected with an OR gate. So we come up with an OR gate. And the output of our OR gate is indeed Y. So this is how you develop a combinational logic circuit from a truth table. You go on to a K-map and you come into a combinational logic circuit. So if you remember, I did mention that there is another way that you can draw this K-map. So this is horizontally, and what about a different way? So let's try out a different way as well. So now we have another truth table over here, but I told you that we will be developing the K-map a little differently. So we can also switch this with 2 columns and 4 rows. So how do we exactly do this? Let me show you. So in this case, I'm having A to be over here, our columns, and we have B and C combination over here. But just to let you know, we can also do it having A, B together over here with C separately. So remember, there is no exact specific way to do this. Just make sure this is due to the associative law in Boolean algebra. So let's just go ahead with this particular manner. We can have any combination. We can have A, B, C, or A, B, and C separately. Associative law, remember? So A has 2 possible options of being 0 or 1. BC has 0, 0, 0, 1, 1, 1, and 1, 0. So remember, 1, 1 has to always come before 1, 0 because of gray code. And let's fill this up with our output. We see that it's easier if we just fill in when the instances are true. A 0, which is this particular column, and BC takes 0, 1. 0, 1 is this particular box. What do we fill in there? We fill in a 1 over there. And we have 1, A is 1, and 1, 0. This particular point. And we have A being 1 and BC being 1, 1, which is this particular point. We'll fill the rest of the combinations with 0. And now we got the task of grouping this. Like I mentioned before, we prefer large groups. So over here, our only possible option is 2 ones together. And this isolated 1 has no other one to be grouped with. You see that this one has another one very close by, but always remember, you can never group diagonally. This is wrong grouping. So this one, like we can see, cannot be grouped with any other one but themselves. So let's just do the grouping like this. So coming off with the Boolean expression for this isolated one, we see that A is a constant of 0, which is complement of A, and B and C is also a constant of the complement of B and C. That is the expression we come up. And over here, we got A as a constant of 1, which is just A, and the combination of B and C, you see that B does not change. B is a constant, but C keeps changing. So we just have a B over there. So coming up with an expression for this particular truth table, we see that the output Y is the combination of AB, which is A and B, or A prime, B prime, C. So how do we come up with a combinational logic circuit for this particular instance. So just like before, we have to come up with our three input variables, which is A, B, and C. We have A, B, and we also have C, and we also have the complement of each instance. Our first combination, which is A and B, we have A and B with an AND gate, and we have the complement of A, which is coming out of the NOT gate, not A, not B, and C, coming out of C. These three, once again, go into the AND, and together they are OR. That is exactly our output Y. So this is not really hard. And I would also like to move on to 4 input variables. How do we deal with that? So now we have the task with a truth table of 4 input variables, namely A, B, C, and D, and we have one output variable Y. How do we come up with a K-map for this? So when we had two input variables, we had 2 rows and 2 columns. And when we had 3 variables, we could either go with 2 rows and 4 columns or 2 rows and 4 columns. In this particular case, no matter which order we go to, we have 4 input variables. So we will be having 4 rows and 4 columns. So let's go ahead and develop the K-map for this case. 4 rows, 4 columns. So filling out the input variables, remember that we do not necessarily have to stick to an order. We can have A, B over here and C, D over here. Doesn't matter as long as you make sure all of the variables you fill in correctly. Or we could also have something like CD over here and AB on top. Does not matter as long as you make sure that the constant for C or the constant for D is the same as the combination given here. So for example, you see that when CD is 1, 0. So let's just fill it out over here. 1, 1, 0, 0, 0, 0, 1, 1, 1, and 1, 0. So let's just take an arbitrary column. Let's just assume we are talking about this particular case. All right, so we have AB being 0, 1, AB being 0, 1, which is this column, and CD is 0, 1 as well. That's this. So we have this particular value. But now let's change this where we have the different, we have AB over here and CD over here now. So AB is 0, 1, that's this, and CD is 0, 1, that's here, and we have 0 over there. So just remember, no matter which order you take it, you're going to end up with the same. So let's go ahead and fill this out. So I think we should go ahead of filling the ones where it's true. So 0, 0, 0, 0 is 1 over here, and AB 0, 0, and CD 1, 0. That is this. And this low, AB 0, 0, and 1, 1. 0, 0, 1, 1 is this. And we have these three. We have 0, 1, 1, 0, 0, 1, and 1, 0. That's here. And 0, 1, that is this column, row. And 1, 1, that's here. And 1, 0, that's the last row. And 0, 1, 0, 0, 0, that's here. And we have one more where it's 1, 0, 1, 0. So 1, 0, 1, 0 is right over there. So the rest of the columns, we just go ahead and fill them out with 0. And how do we group this? So grouping this, just when you see it, you should see that you have a group of 4 ones. Now this is really great. You can just go ahead and group that together. And you have a isolated one over here, you have one over here, you have one over here, and you have one over here. So remember, I told you the K-map is not just limited to this, but the K-map can be grouped because it is being continued. So this one could be grouped with this one could be grouped with this one. So can this be grouped together? This one and this one. So with that in mind, we see that we can group this one along with this one and this one. So we have 4 ones grouped together once again. So how do we come up with an expression for that? So this, you have to be very careful now. Let's go ahead with our first group. You see that A, along the rows, B is not a constant, but A is a constant of 0. That is A prime, the complement of A. Along the columns, C is a constant, but D is not. So we have C. And for this particular group of 4, along the columns, we see that C keeps changing, but D is a constant of the complement of D, which is 0. And along the rows, A keeps changing. We're looking at this row and this row. A keeps changing, but B is a constant of the complement of B. That's the complement of B. And when you look at this particular column, you see that you have not C, D prime. You have D prime over there. So finally, we have simplified this as much as possible to get the Boolean expression A complement and C, or complement of B and complement of D. How do we come up with the combinational logic circuit for this? Very easy. We just have to draw out the possible input variables, which is A, B, C, and D. And now we just have 2 combinations, you can see. Complement of A, which comes out of this, and C, normal C, and both of these into an AND gate. Let me draw that nicer. Have AND gate over here, together with the complement of B, which is this, and the complement of D, which is this point. You have an AND gate over there, and both of these into an OR. So that is your output Y. It's as easy as that. You have a complicated 4 input variable, but your K-map can be used to simplify this Boolean expression, just 2 combinations with this easy grouping method. So I hope K-maps, combinational logic circuits, was easy for you now. And let's move on to how you can come up with a truth table with your K-map is given. So where we'll dive into determining a K-map when your Boolean expression is given. We have this Boolean expression, and we see that we have 3 input variables, which is A, B, and C. And when you know that you have 3 input variables, we know that we can come up with either 2 rows and 4 columns, or 4 rows and 2 columns. So let's go ahead with this combination where I have 2 rows and 4 columns. So I have A and I have B and C. We have 0, 0, 0, 1, 1, 1, 1, 0, and the 0, 1 for A. So let's go ahead and fill this out, right? So filling this out should not be an issue. So we have A, B. So let's write down this expression. You have A, B, A and B, or A prime, B prime, and C. So in this case, our first particular combination, A is 1, B is 1. Where do we have A1 and B1? You have A being 1 in this row, and you have B being 1 in this particular column as well as this particular column, right? So if you do see the two overlapping instances, you see that you have this square and this square where you can fill out with ones. Let's go ahead and do that. 1, 1. Next case, we have the complement of A where it's 0, B is 0, and C is 1. Square is going to have this combination. So A, the complement of A where A is 0, is this particular row. And the complement of B, where is B 0? This, and you have this. And your C has to be 1. So let's go ahead with the combination of that. So have this row, and your BC has to be 0, 1. Where do we have 0, 1? 0, 1 is exactly this column. So we have one particular square, which is this, where we need to fill out with A1. Rest of the squares, just keep adding zeros. So this is going to be your K-map when your Boolean expression is given. If you go back and check out the previous example that we did, you'll see that this is exactly the K-map we obtained in that particular exercise as well. Example where you have the Boolean expression and you need to come up with a K-map. Now in this instance, you see that we have 3 input variables, which is A, B, C, and D. You know that when you have 4 input variables, you're going to have a K-map with 4 rows and 4 columns. So let's straight away draw a K-map where you have 4 rows and 4 columns. Just easy as that. And like I said, you can come up with a combination A, B, and C, D, or you can switch these two, does not matter. You come up with same correct answer. So we go ahead and fill this up. In this combination, you have A, B plus complement of B, D, and C. Talking about the first product, you have A, that's 1, the value of B is going to take 1. Why do we have A and B being both 1, regardless of the value of C and D? So 1, 1 is this particular row, right? Regardless of the values of C and D, you have 1, 1. So you just fill that up with possible values. And then you have the combination of the value of B being 0, D is 1 here, and C is 1 here as well. Where do you get this combination? Let's first check out this. So this is our row, and this combination is our column, right? So let's go ahead with that. B has to be 0. Where is B being 0? That is this row and this row. So we have 2 possible rows, and the column where the values of D and C is going to be 1, 1 is just this. So we see that we have 2 possible squares, which is over here and over here. So let's fill that up with 1s. 1, 1. So the rest of it is basically 0, where you have false. It's exactly the K-map. So if you want to, you can go ahead and group these and see exactly what you come up with. You're going to come up with the same Boolean expression. So just to give you a heads up on how you can do this, you can group these fours together and you can group this particular one and this particular one together. This is going to give you A, B, and this is going to give you P prime, D, and C. So this is how you tackle Boolean expressions to the development of Q-maps. Easy as that. With all of that in mind, I would like to thank you all for watching my video, and please subscribe for more videos that are entertaining and also super educational.